question regarding the supplement, the mathematics review and the supplement. Problems with the unit, simplify each mathematical expression. Go down to number 4. Number 4, the units here are a little weird. Microliters squared, which is, microliters is a volume unit. If you square a volume unit, what is that? And so, sometimes the units are a little weird in this, so I didn't really emphasize any of these problems. Like foot-pounds is a unit of torque, miles per hour is okay, inches and feet, lots of people add this without regard for the units. We've got to convert them. Here we have a very bizarre unit, microliters squared, which is just weird. It's a weird unit. I don't know what that is, in terms of volume squared. But anyway, that's what we have. If we take the square root of that, raise it to 1/2 power, then it's okay. And so this one, we can do the units first. Microliters squared to the 1/2 power will be, it's going to be 2 times 1/2 will just give us microliters. And so the units work out okay for the product, but it's just a weird problem in itself. Okay, so we have microliters here. Then what we'll do is we'll just take 3.6 times 10 to the 5. There are 2 ways you could do that. I often do it this way when I input it in the calculator. I'll just show you. Is it working? Oh, this is working. Right. All right. So there are 2 ways I would do that. One way I would do that is just 3.6 times 10 to the minus 5. No, sorry, 3.6 times 10 to the positive 5. 3.6, okay, then we hit this EXP or the EE key or the times 10 key, and so this is E, which means times 10 to the positive 5. That's 3.6 times 10 to the positive 5. And then we could just square root that. This is a different kind of calculator. If you have a TI or something like that, you punch in the number and then you hit the square root key. If you have a Casio or something like this, then it's different. And so what we have to do with that is we just set it up like we set up a normal problem. This will be the square root of 3.6 times 10 to the 5. 3.6 times 10 to the 5. And then hit 600. And so this would end up being 600 microliters here. Okay, the other way we could do this is like this. I would do, let's clear that. I would do parentheses, and then this is what I often do for things. I'd do the 3.6. Now you can type this into the computer. I'll just type in E. That's rather than hit the EXP key. It's quicker for me right now. Times 10 to the 5. Okay, that's okay. Oops. Then I'm going to raise this. Okay, I need to close the parentheses. All right. Close the parentheses, and then I'm going to raise this using this little half here to the 1/2 power. Sometimes what I'll do is I'll enter the fraction, like 1/3. If you raise something to the 1/3, right? There are 2 things you can do. If you have a cube root, which I don't have a cube root key here, it avoids round-off errors. And so if you write it in fractional form, like 1/3, you don't have to round. If you write it in decimal form, you have to round because 1/3 is going to give you 0.3333, and eventually you're going to cut off the 3's, right? At least a round-off error. And so oftentimes when I have a fraction, let's say I'm raising it to the 2/3 power, I raise it to the 2/3 power, I'll just type in 2 divided by 3. That way I don't have to go 0.6 and then eventually round it to 0.7. Or, we know 1/2 is 0.5, so I can type in 0.5 in there. But, that's the case where we have it round up there. It didn't work. Oh, yeah, okay, okay. Thank you. Well, I guess I can't do what I just did. In Excel, you would do it, you just type in ET, which doesn't need
word carrots, what does that mean here? Exponent? Like a little line?
Yeah, it would be the exponent, but I want scientific notation. And so this would be 6. Oh, can I edit this? I guess not. Oh, good. I can't edit this. Well, unfortunately, I would have to do it like this. I'll just clear it. I'll do 3.6. Maybe it's capital E.
Yeah, it's the capital E. We've already used them.
Okay. I got you. All right, this would be 3.6 times 10 to the 5. And then let's raise it to the 1/2 power. Answer 600. So that'll work. So 600 microliters, but we have to worry about sig figs. And so if we go back to the original problem, how many sig figs do we have here in the original problem? Looking at the original problem, we have 2 sig figs. Well, when I look at this, it's ambiguous. It's going to be 1, 2, or 3 sig figs. So, you know, usually people would think, well, actually more. Usually people would think this is 1 sig fig. You know, it's anywhere between 550 and 640. So it's 3 sig figs. It's 600. You know, plus or minus 1 or plus or minus 1/2, or infinite sig figs. I wouldn't necessarily think this is infinite sig figs because this looks like some kind of measurement. And so what we have here is 2 sig figs. And so how can I show this clearly so that 600 microliters has 2 sig figs? Scientific notation. So the correct answer for this is not 600. It would be 6.0 times 10 to the 2 microliters. No, it's 600 microliters. 2 sig figs. All right, the other problem here was number 6. Is it correct? So we have an order of operation. What should I do? Should I cube everything in the parentheses first, or should I divide first? I got to cube everything. And this means I have to, well, whatever's in the parentheses, so I have to cube the number and the units. And so let's look at the dimensions first. If I have milliseconds divided by milliseconds cubed, I'm going to end up with milliseconds to the minus 2, or 1 over milliseconds squared. And so the units here I have are milliseconds to the minus 2, which is a very bizarre unit. This is one reason I don't really like this math review, because the problems are exotic. You know, these aren't your typical chemistry problems. See, and so I didn't even say to do this actually, but it's good, you know, for review for sure. All right, then we got to cube this one. Well, if we cube this one, it's going to be, is it going to be 4 cubed, 10 to the 18 cubed? Or what? How should I do that? Well, you just do it in the calculator. It's probably the easiest. In fact, I just do it all together. So let's use a calculator that's more like your calculator. Let's see if this one. Yeah, this is more like your calculator. Oops. See that here. So let's try this calculator to do this. And so let's do the numerator is 6.45 times 10 to the minus 35. And so I just type in 6.45, 45. Okay, times 10 to the minus 35. Wow, that's a really small number. And so, is this the key I use here, the E key? Let me No. No, what's for scientific notation, which one should I use? Should I use this key here? No, I don't want to use this key because this key will set me off by a factor of 10. So, is there a scientific notation key here? Interesting. A scientific calculator that if I use this key, then I have to do times this. I can't just hit this. And anyway, this has a reverse. So all these calculators. Does this have a scientific notation key? The EXP key here. And so let's try this one. 6.45 times 10 to the minus 35. So I wonder if this, no, it doesn't work either. 6.45 times 10 to the minus, oops, 6.45 times 10 to the, this one you have to put the number in and then change the sign. My calculator, I change the sign and then put the number in. This just goes left to right. And so this is like a TI. Times 10 to the 35 negative. Oops, that's not the right key, sorry.
Plus or minus.
The plus or minus key here. Alright, one more time. 6.45 times 10 to, let me see it. Can I do that? No, I can't change it. 35 negative. There it goes, finally. Divided by 4 times 10 to the 18. And so what I do here is I just do, I would just do this. Divided by 4 times 10 to the 18. Now you have to be aware of how your calculator handles inputs. To be ultra safe, I would do this. I would put this in parentheses. 4 times 10 to the 18. This. And then I need to cube that. So I'm going to close the parentheses and then cube it. When I close the parentheses, it didn't work. And so this problem is actually, I guess it's good because you can check your answers. And so you can get a decent calculator here. So 6.45 times, so for TI calculators, I'm looking for the double E key. The double E key or the EXP key. Oh, no wonder. I thought this was a TI calculator. This is an HP calculator, sorry. This looks like an HP accounting calculator. This will be a sharp. Alright, so 6.45 times 10 to the, okay, we have an EXP key here, times 10 to the 35, and then we go negative. Oops, why did it go to 1? 6.45 times 10 to the negative 35. Okay. 6.45 times 10 to the negative 35 divided by 4 times 10 to the 18 cubed. And so I do divided by 4 times 10 to the 18 cubed. Now what if I do this? I'm just going to hit the y cubed key here, or the x cubed key. Ready? See if it'll work. And then equals. So I have 1.007 times 10 to the minus 90. Let's write that down. 1.007 times 10 to the minus 90. That's more 6/8 than I'm allowed. All right, now I'm not sure if that worked, that bottom worked, because it depends on the calculator, how you input the cube there. And so I'm just going to double check it. I'm going to double check it by going 6.45 times 10 to the negative 35 here. And then I'm going to divide it by parentheses for exp 18. Okay, and I'm going to close that parentheses and then cube that. And I get the same number. So it worked. I didn't need the parentheses. The parentheses were just extra steps that were not necessary, and that would slow you down on a test. And so, the faster you can key these in, and I've seen people on tests, I see them key so many keystrokes in there. I'm wondering what are they doing? And then I finally figured out what they were doing. When they were doing scientific notation, they were not using the exp key. They were just manually inputting it, like 1.3 times 10 to the x, and then input the x. And I was thinking, wow. So it was taking them like 2 to 4 times longer than other people. And so it makes a big difference about calculator input. But anyway, this is our answer here. And so how many sig figs are we allowed in this particular problem? How many sig figs do I have here? How many sig figs here? Just one. So I'm only allowed 1 sig fig here. Going to 1 sig fig leads to usually the big round off error. So what I like to do, if there's only 1 sig fig allowed, I'd like to kind of subscript things just to carry some extra. This way, if those numbers were exact, then it would be closer to this rather than rounding. In this case, it's close, but in other cases, it's not. So, for example, if you had 1.49, what would that round to? 1.49 would round to 1 sig fig. It would round to 1. Yeah, and so let's say somebody, I need to borrow $1.49. So, I'll borrow $1.49 from you. I'm going to pay you back $1 because, $1 is the same as $1.49 because it rounds to $1, And so that's what we call round off error. I'm going to try to avoid that as much as possible, but sometimes not. All right, let's look at the next one here. This is a problem I like here. I like number 4, I like number 5, I like those. Number 3's not bad. Number 2's not bad. In fact, these all look pretty good. Microliters and milliliters, square feet and millimeters square. These all look pretty good. Some people have this conversion factor memorized. Do you know how many liters are in a cubic meter? A cubic meter is like, well, here's a meter stick. So a cubic meter is like this long, this tall, this wide. Just a cubic meter. So how many liters do you think you could fit in a cubic meter? Would you say 1,000? Or no, maybe let's go back. Would you say 100? You could fit 100 liters in a cubic meter. Actually, how many people think 100? Okay, how about 1,000? How many people think 1,000? 1,000, okay. How about 1 million? How many of you think you can fit 1 million? Or actually, I skipped one. 100,000. 100,000, okay. 1 million? No. Well, we'll find out. So let's do this one first. 2.8 pounds per cubic foot, grams per liter. Pounds per cubic foot. No, that's not really that common. I mean, most science people aren't working with cubic feet. Well, we'll try anyway. Actually, did anybody get this one already? No? So let's go with the 2.8 pounds per cubic foot. This is our given. Our given is actually a ratio. Normally this is would be a conversion factor, but we don't have anything else given, so we're going to start with this. This is our density in pounds per cubic foot. Now, going to do here. Now you have a choice. When we have a numerator and denominator that we need to change, you can start with one or the other. It doesn't matter which one you start with. So I need to get rid of pounds. So what should I get rid of? You know, the other thing, the other thing about this mathematics review is it doesn't have enough variety. You know, what type of problem is missing when you look at this? You know, these are all the dimensional analysis problems here because then we go to logarithms. What type of problem is missing from the dimensional analysis? So when you see this list of review problems, you might be deceived into thinking, you know, that we don't have to worry about what it is. You know, what is this stuff? 2.8 pounds per cubic foot of what? .8 pounds per cubic foot of what? And so that's something that's missing because we like to know what the substance is or what the mixture is. You know, substance, is a substance a mixture? Normally when we think about substances, we think about what the earth is made out of, the universe is made out of, that type of stuff. But is a mixture a substance? Seems like it because everything's made up of substances, right? This substance, that substance. But it depends on how you define it. So is a mixture a substance?
Well, substance is pure, right?
Yeah, it's a quirky definition. Substances are pure by definition; they're pure, and so the only things that qualify as substances are elements, which are pure, and compounds, which are pure. Everything else is a mixture. Well, anyway, let's go back to this. So we got to get rid of pounds. Eventually, we want to go to grams. So how can we go from pounds to grams? We could go to kilograms and then kilograms to grams. I like the kilogram conversion rather than the gram conversion. It's just easier to remember. If you're doing, you can go straight from pounds to grams. You know, it's 453.6. It's a little bit harder than remembering 2.20. Is it 2.205 or 2.204? I don't even remember. Do I have to remember that one? Did I say you have to memorize it? No, you don't have to memorize that. That's a given. Well, I mean, I can give it to you. 2.2. Wait, over down here, 2.205 pounds per kilogram per kg. All right, so that takes us to pounds of whatever the substance or mixture is, and then we'll go from kilograms to grams. 1,000 grams in a kilogram. Kilos, 1,000. And so we converted the top. If we convert the top, then we just have to convert the bottom. When we convert the bottom, we got to get it to cancel out. And so we want foot cubed to cancel out. Do you know any conversion factors with foot cubed? No. But you'd say, okay, I don't know it, therefore this must be a given. But it's not going to be a given. This one you have to be able to figure out. What is it? We go from feet to inches. We go from feet to inches. This is not going to be given because everybody should know the definition here. 12 inches in a foot, 1 foot is 12 inches. Everybody should know that. And so, are there 12 cubic inches in a cubic foot? Are there 12 cubic inches in a cubic foot? No. Are there 144 cubic inches in a cubic foot? No. Are there 720 something cubic inches in a cubic foot? Yes. Right, because it's 12 cubed. 12 times 12 times 12. So The grams stay, but now the cubic feet cancels out the cubic feet, so I'm canceling out the denominator in this case, so that's why I have it this orientation. And so this gives me grams per cubic inch. I don't want grams per cubic inch, I want grams per liter. And so then I'm going to go from inches to what? Inches to centimeters. In 1 inch, how many centimeters are there? 3.54, and then we'll just cube the whole thing. And so inches cubed cancels, that leaves me with centimeters cubed, and then where do I go from centimeters cubed? I'm sorry? Yeah. But it's easier to remember. A centimeter cubed is the same thing as a milliliter. So do I need to cube this whole thing? No. This is already by definition. I don't want to cube this. 1 centimeter cubed is equivalent to 1 milliliter. Milliliter is a volume unit, centimeters is length. So we've got to cube length. But we don't want milliliters, we want liters. So here, there are 1,000 milliliters in a liter. So milliliters cancels, and that gives us units of grams per liter. Normally when we're talking about densities, gram per liter densities are usually for gases, because they're kind of low density. Oh, okay, so the dimensions work out. We have grams per liter of whatever this stuff is, and then we'll just punch it out in the calculator. Let's do it here. Let's see. And so I'm going to go 2.8 divided by 2.205 times 1,000. I just go in order here. Times 1,000 divided by 12. Oh, that's 12 cubed. Do I need parentheses around this? Do I need parentheses around my 12? No, I don't. I could save time by not doing parentheses. I'll just cube it. Boom. It's 12 cubed. Divided by 2.54. Again, I don't need the parentheses. I'm just going to cube it. Times 1,000. 44.84. 44.84 grams per liter. Now, I would check the answer, in the back and compare, or I would double check my calculation. Usually go through my calculation again. Did anybody else get this answer? Yeah? Okay, good. How many sig figs are we allowed? 2. And so we're going to have to round this. We'll round this to 45 grams per liter. 45 grams per liter. That's odd density. It's a very odd density. Because, you should have some reference point densities in your mind. Like the density of gold. Density of gold. Density of gold is about 20 grams per milliliter. The density of copper about 9. Density of lead is about 11. Density of mercury is about 13. Density of water about 1. The density of helium about 0.001, or about 1 gram per liter. So helium has a density of 1 gram per liter. Air, what is the density of air? Air is a mixture. Can we get the density of a mixture? Is that possible? We have to talk. Are we talking dry air or
You think the gases will multiply to the atom what? If it's three, if it contains three.
Yeah, we would do that. It's in kilograms. Oops, here we
Oh,
go.
that's chapter 5, right? Chapter 5.
Chapter 5, right?
Multiply.
You do this very similar thing to what you do for that.
Multiply,
Exactly.
add them up.
Right, depending on what percentage is. Exactly, that's how you calculate the density there. I don't, unfortunately, the density is 1.225 kilograms per cubic meter. Kilogram, when people start using all different units for densities, it's hard to compare. This is why some people like STP, because they have some standard reference points. All right, but you know, this kilogram per cubic meter, you could do some certain things. Like, for example, how many grams would that be? If it's 1.225 kilograms, how many grams is that? That would be 1,225 grams, right? And then we ask ourselves, you know, in a cubic meter, how many milliliters are there? Well, this is cubic meter. I ask you how many liters are in a cubic meter. Right? That's a question. And so let's look at how many liters are in a cubic meter. And so if I have 1 cubic meter here, let's calculate how many liters there are. And so we'd go from cubic meters to what? To centimeters. And so going from cubic meters to centimeters would be meters to centimeters. How many centimeters in a meter? 100. And then we have to cube this. And so that's that. And then, well, we'll stop here. We'll stop here because this is related to this question here. In a cubic meter, how many cubic centimeters are there? In a cubic meter, which is this, how many cubic centimeters are there? 1,000? A million? A million?
Yeah.
A million's correct. There are 1 million cubic centimeters in a cubic meter. Oh, we can see that here. Cubic meters cancel. And this is 10 squared cubed. 10 squared cubed is a million. So there's 1 million cubic centimeters is equivalent to a cubic meter. But then, you know, the original question was how many liters there are. And so the majority, you said 1,000. So let's see, is that correct? And so as far as cubic centimeters go, you know, we have, we can convert this from cubic centimeters to milliliters. I mean, convert it to milliliters, 1 to 1. And then from milliliters, we can convert it to liters. So 1,000 milliliters per liter. And so it comes out to 1,000 liters. And so there are 1,000 liters in a cubic meter, and there's 1 million milliliters in a cubic meter, or 1 million cubic centimeters in a cubic meter. And so even though this unit looks so strange, do you know what this unit is? Take a look at this unit and convert it into your head, right? Are you ready? Okay, let's convert kilograms to grams. Converting kilograms to grams, we'll just multiply it by 1,000, right? And so if it's 1.225 kilograms, that's 1,225 grams. Now let's go from cubic meters to liters. If we go from cubic meters to liters, we multiply by 1,000, right? Because there are 1,000 liters. And so we multiply the top by 1,000, we multiply the bottom by 1,000, and this funny unit, which is a kilogram per meter cubed, is actually a gram per liter. Gram per liter is the typical units we use for gases. You know, gases have a density on the order of grams per liter, right? Helium is about 1 gram per liter. Or in terms of grams per milliliter, it would be 0.001 grams per milliliter. And so here it's 0.001225 grams per milliliter, or in scientific notations this. And so the units are a little bit tricky, but after you work with the units for a while, then you can see there are a lot of ways of expressing things. Like, for example, have you ever read your water report from the municipal water district?
No.
They use, oftentimes they'll use this unit. So hopefully your water is not like this, but sometimes they'll use like something like this: 1.8 micrograms of lead per liter. What is that? Is that micrograms of lead per liter of lead? No. So this is. I asked you what type of problem is missing from this. The type of problem that's missing from this is, you know, to identify the substance, because here it's kind of critical. It's not per liter of lead; it's per liter of water. And so when all of a sudden we have two different substances in there, we've got to keep track of these things. Right? If you don't keep track of these, then it's so easy to get the wrong answer. Well, I guess it's break time. Is it break time? What time did it start? 2:30? Oh, no, it's not break time yet. Go ahead. When you look at this, do you see what the unit is? What is the unit? Express this in the unit that's more common. Okay, how about this? How many? Okay, you know what? 1,000 liters weighs about how many grams? Okay, or sometimes they'll do this. Microgram per liter. This is actually, or sometimes they'll do. I mean, this wouldn't be so healthy. Microgram of lead per milliliter of water. And so if you had 1 microgram of lead per milliliter of water, wow, that's high. This is a little bit better, you know, because a liter is bigger, and so you don't want that much lead in your water, right? And so this is actually a lot less water. How much lead is that? How much lead that is this. You know, the units are kind of funny, but you know how much a milliliter of water weighs? About? What's the density of water? Density of water. Yeah, to 3 sig figs is 1.00. To 4 sig figs, it falls off there. And so we know that water, drinking water, is going to have a density of about 1.00. So hopefully it's not too contaminated. And so for every milliliter of water, we have about 1.0. We'll just go with 1.0, maybe 3 sig figs should be okay. We have 1.0 grams of water. And so when I look at this, I'm looking at, wow, you know, this is actually 1.8 micrograms of lead per gram of water. So if you have a gram of water, we've got 1.8 micrograms of lead in there, right? But then again, when I look at this, you know, how many micrograms are there in a gram? Are there 1,000 micrograms in a gram? 100,000 micrograms in a gram? 1,000,000 micrograms in a gram? How many micrograms in a gram? 10 to the 6, and 10 to the 6 is also known as a million. And so, well, okay, so we can say this: for every gram, there is going to be 1,000,000 micrograms. The grams of water cancel, that leaves me with micrograms of water. Now take a look. We have 1.8 micrograms of lead per million grams of water. Does that kind of ring a bell? In a way? What would you call that? That's right, you call this 1.8 ppm. 1.8 ppm lead. And so normally the units that they use, they could use micrograms per milliliter, or they could use milligrams per milliliter, or milligrams per liter. Let me tell you this, a milligram per liter is the same thing as a microgram per milliliter, which is the same thing as a ppm. And so all these units, many of them are just the same thing. They're just different ways of expressing the same thing. Okay? So some people have these additional conversion factors memorized. If you have these additional conversion factors memorized, you got to show it. Just write it on a piece of paper. And so here, some people will know that there are 1,000 liters in a cubic meter. Let's multiply that by 1,000. All right. Were there any other questions? This is not. What is this? You recognize this unit?
Liter. It's a liter, right? So,
It's 1.8 micrograms of lead per liter of water, which means what? Which means this is parts per billion. This is parts per billion. How did I know? Well, this is this is 1.8 micrograms per 1,000 milliliters. Right? Is that right? No. Maybe. Per 1,000 grams, let's say. And then how many micrograms are there in a gram? 1 million. And so what's 1,000 million? 1,000 million is if you have 1,000 millions, you'll have a billion. Therefore, it's parts per billion. Yeah? And so, obviously 1.8 parts per billion is a lot better than 1.8 parts per million for lead contamination in water. And so take a look at your next water, if you get those water, or you could just go online and see what the water quality is for your particular municipality. Yeah. I don't know why they did it. When I looked at it, I thought, okay, why are they using this is a common unit in chemistry, but most people are familiar with parts per million and parts per billion. When EPA writes their standards, they usually write it and express it in parts per million and parts per billion. For example, carbon monoxide exposure, 10 parts per million, et cetera, et cetera. And so I think it's just to have it one step removed from that. Well, anyway, we're on chapter 5, so let's go ahead and finish up chapter 5 here. All right, chapter 5, continuing with atomic theory. And so what are atoms made of? Protons, neutrons, electrons. Did I talk about Rutherford? What did Rutherford do? The gold scattering experiment. And What did the gold scattering experiment determine? Yeah, the internal structure of the atom. And what was the internal structure of the atom? What's that model called? This is the Rutherford scattering experiment, the gold foil experiment. It's a very famous experiment that determined the structure, the internal structure of the atom. The internal structure of the atom, we call it the plum pudding. It's not the plum pudding, it's called the what's that thing in the center of the circle there? The nucleus. So it's called the, let's just do something with this, because the plum pudding model did not have a nucleus. The plum pudding model, whatever was in the nucleus is spread out over the entire volume. That was the gel, or whatever they called it, a positive charge. And so this model is called the nucleus atom model. Nucleus atom model? No. It's called the nuclear atom model. Nuclear atom model? Well, does it sound right? Nuclear atom model? No? It's called the, it's not called the nuclear atom model, it's called the nuclear model of the atom. That's what, no wonder you get it. But, no, it doesn't matter, it's just the nuclear atom model, or whatever you want to call it. And the nuclear atom model, or the nuclear model of the atom, there's a nucleus in the center. And the nucleus in the center contains all the what? Protons and neutrons. The protons contain all the positive charge in the atom, and so the nucleus contains all the positive charge. And the protons and neutrons together contain most of the mass of the atom. And so what is the approximate density of the nucleus? Density of the nucleus. So, well, let's take a look at the atom again. The atom's mostly, this blue area is mostly what?
Empty space.
Empty space. And electrons are dispersed in this blue area. And the nucleus, you know, actually, this is what it says. If this were 1 centimeter in diameter, nucleus, then the atom itself would be like a football field. Huge. And so this contains most of the mass and is packed into a tiny volume. And so the density must be very high. Higher than 20 grams per cubic centimeter, which is gold, or lower than 20 grams per cubic centimeter? Much higher? Lower? Well, let's take a look at gold. When we measure the density of gold, we're weighing it for particular volumes. So let's take this thin sheet of gold foil. What we do is we measure the volume. So the volume we measure out to here, right? We dip this gold foil in water, measure out to here. Do you see these empty spaces between? Those empty spaces are called void spaces. There's no mass there. And so what we have is mostly empty space, but this whole thing weighs 20 grams per cubic centimeter, or 20 grams per milliliter, including all the empty space here and all the empty space here. Okay. If we get rid of all the empty space, that is, if we just take all the nuclei and then collect those into a beaker, And so we get rid of all the empty space and only have nuclei. What do you think the density of the nucleus is? I mean, it's hard to imagine this, but it's on the order of tons. On the order of tons per cubic centimeter. So can you imagine putting a ton of matter into a milliliter of volume? You know, that's how dense it is. So it's like incomprehensible, the density. You know, but that doesn't stop people. You know, that doesn't stop people from writing that as an answer. You know, what's the density of water? 426 times 10 to the 3 kilograms. You know, and some people get caught up in these numbers. Well, they might not be that extreme. It could be like 426 grams per milliliter. 426 grams per milliliter. Let's see. That makes it about 20 times more dense than gold. So water is 20 times more dense than gold? No. And so we have to pay attention to the numbers. Why bother registering some numbers in your mind? The reason is so that you don't come up with ridiculous answers that you know, the people will just be shocked. You know, what are you talking about? But you think it's okay because it's just a number, you punched it in your calculator, and that's what the calculator told you. Right? And so be careful, because this happens at scientific conferences. Not so much, because people get embarrassed with split times. No. But anyway, so this is the nuclear atom model, the nuclear atom. And then these are the results from Rutherford. Did we already talk about Rutherford pretty much? Yeah. Okay, so let's try to use some of this. You know, I know one property of the atom. One property is the mass. Well, we can see why the masses are different. The masses are different because they contain, you know, atoms contain different amounts of protons and neutrons. And so, for example, deuterium, which is hydrogen 2, weighs about twice as much as hydrogen 1. Does the mass impact its chemical properties? Yeah. No, it's physical properties, yeah, but not its chemical properties. And the mass, no, it doesn't really correlate. And so let's look at some other stuff. Well, one of the first things we'll look at is something like this. So let's take a look at hydrogen 1. Hydrogen 1 consists of, what's the composition of hydrogen 1? 1 proton, 1 electron. The proton's a positive charge, the electron's a negative charge, so I'll write P positive. The nucleus is here. Inside the nucleus, so I have just 1 proton, that's it. And then surrounding the nucleus is empty space in which the electron is free to roam, basically. So this is our model of the hydrogen atom here. It's got 1 proton. This proton is kind of big. You know, and this drawing's not to scale, because if this proton's about 2 centimeters, how big should the atom be? If this proton's about 2 centimeters, then the atom should be about 2 football fields. But I'm not gonna walk out there and walk out of there to draw it. It would be just too big, right? And so really I should draw the nucleus as a tiny dot in the center of this. But it's okay, I'm gonna exaggerate this. And so what we're doing is we're gonna go to helium. Helium, we'll look at helium-4. What's the composition of helium-4? Helium-4 has 2 protons. What else? 2 neutrons and 2 electrons. And so in the nucleus, we're going to have, actually I need to draw this a little bit bigger, 2 protons, 2 neutrons. Now, it's going to weigh a lot more. Helium-4 weighs about 4U, you know, because the electrons don't weigh much. And the protons and neutrons weigh about 1U. And the hydrogen weighs about 1U. And so the helium is going to be about 4 times heavier than the hydrogen atom, right? And therefore, is it 4 times bigger? If helium is 4 times heavier, is it 4 times bigger? You'd expect it to be 4 times bigger. It's got 4 times as much stuff. but it's not. It's smaller, right? Helium's smaller. And so what we gotta do is, we gotta understand this. Well, do electrons like each other? Electrons don't necessarily like each other. Why not? Yeah, the charge is the same charges repel. And so since both electrons are both negatively charged, they kind of stay away from each other as much as possible, but they're moving around, so sometimes they'll cross paths or whatever else. Are electrons big or electrons small? No, electrons don't weigh much. They weigh about 0.005 U. That's not much. So how big are they? I said electrons are about 2,000 times lighter than a proton or neutron. Does that mean they're 2,000 times smaller in physical size, in dimension? Is an electron a spherical particle? You know, like they showed the protons and neutrons. They showed the protons and neutrons here. And they showed the protons and neutrons as little spherical particles like atoms. Is that accurate? Or is that just some conceptual drawing? It's accurate? And are the protons and neutrons arranged in a nucleus like this? Well, you know, those are questions best left to the particle physicists and nuclear chemists.
Did you say it's precise?
No. But let me tell you, the physicists and the nuclear chemists, they're trying to come up with the theory of the nucleus. They want to know the composition and the structure of the nucleus. And so what they're trying to do is they're trying to break apart protons and they're trying to break apart neutrons into smaller and smaller pieces. And so this is out of the realm of chemists, because chemists, you know, when we have a chemical reaction, the atoms are just rearranged. The atoms don't transmutate into other elements. And so the electrons don't like each other because they have the same charge. Do electrons like the nucleus? The electrons like the nucleus. Right? So when we look at this one, which nucleus is better? A +1 nucleus or a +2 nucleus for electrons? +2, because it's going to give you stronger electrical attraction. Electrical force. We know that electrical force based on Coulomb's law. If we jump from +1 to +2, what happens to the electrical force? Coulomb's law says that the force is directly proportional to the charge. So if we double the charge, we just doubled the force. And so think about this. There's twice as strong of a pull on the electrons. And so this electron sees +2. It's highly attracted to that. It's going to pull towards it. This electron sees the same thing, +2. It's going to be highly attracted. And so this could be the reason why the atom shrinks. The atom shrinks because of the Coulombic attraction between the protons and the electrons. There's no hard boundary here. This boundary is just kind of the relative size. You know, the electrons can go outside this boundary here. It's just probabilities getting lower, you know, the farther it veers away because it's being pulled towards there. And so this is why we want to understand composition and structure, because composition and structure can be related to properties, and size is a very important property of atoms. Now, well, okay, that is for that's for helium-4. Let's go on. After helium comes what? Lithium. So after helium comes lithium. Lithium has how many protons? 3. So I just have to draw the nucleus a little big here, write in 3 protons. Okay, now it depends on which lithium isotope we're talking about. So let's go with lithium-7. Lithium-7 is a common one. If I'm dealing with lithium-7, how many neutrons do I have? 4. I have 4 neutrons. And how many electrons do I have? 3. Now the electrons, they kind of want to stay apart from each other. One here, let's go one here. But they're moving, so they can cross paths, of course. And so based on what I just said, then lithium should be smaller or bigger than helium? Based on what I just said, lithium should be smaller or bigger than helium? Smaller. And you'd be absolutely right. Based on Coulomb's law, lithium should be smaller than helium. Now, whatever we propose, whatever we predict, has to be verified by experimental fact. It's a fact of nature that lithium is smaller than helium. Yeah, you know what? Lithium is larger than helium. Not only is lithium larger than helium is larger than hydrogen. How could lithium be larger than hydrogen? Is there something going on, here that, is this a violation of Coulomb's law? Can we have violations of laws? Actually, we can. We can have violations of law. Laws are a bit tricky. Some laws you can't have violations of, or people have tried to find violations of, but have not been successful. Let me give you an example. For the past couple of 100 years, people have been trying to violate the laws of thermodynamics, but none have been successful. The laws of thermodynamics have withstood tests of time. But Charles' law, have people found violations of Charles' law? It's a bit tricky, but I'll tell you. Yeah, but it's easy to understand why, and we'll talk about that maybe Thursday. It makes total sense that there would be violations of Charles' law if you understand chemical properties a little bit. But what's going on here? Is there a violation of Coulomb's law? No, there is not a violation of Coulomb's law. You're absolutely right. Lithium should be smaller. It isn't. Why? It's there's something more. There's something we're missing out of the structure, and this is why it's called structure part 1. You know what's missing? Yeah, what's missing is this whole idea of shells. What's missing is the electron. I asked you how big an electron is physically. You know how big? If you asked a particle physicist how big is an electron, what would they say? Like if a nucleus is the size of a golf ball, a centimeter or something, or half a golf ball, then an electron must be the size of an ant. Is that right? You thought it was what?
A nickel or a quarter.
A nickel? Okay, so if the size of the nucleus is a centimeter, then the size of an electron would be the size of a nickel. If the size of the nucleus is a quarter, then the electron would be like a grain of rice.
I don't remember that.
No?
It's just small.
It's just small? How small?
Just disagree that it's small.
Let's just agree that it's small. You go to a scientific conference, that doesn't cut it as an answer. If you go to a scientific conference, someone's going to ask you, how small? How small? Give me some number. And if you go to the scientific conference, you know what they'll tell you? 0. That's how big an electron is. It's 0. Well, how could it be 0? The size of an electron is 0. Okay. Well, what does that mean? It means that electron is kind of weird. And electron, even though we're thinking of this in terms of Coulomb's law, electron behaves strangely. And so we have to go to part 2 of atomic structure in order to understand that. And we're going to talk a lot more about electrons because it's electrons that are causing this kind of weird behavior. Okay? Well, anyway, we'll stop here. We'll take a break and then we'll start again. And so why is lithium bigger? We aren't going to answer that question until we get to atomic structure part 2.